Hello, and welcome to the video going over the fundamentals of AC sine waves. This is for our Unit 15. I don't know why I said 16, this is Unit 15. Going over our fundamentals of electricity book for ICW. Um, this is a presentation PowerPoint that I threw together. I'm going to have a couple little assistant things here, but other than that, everything is pretty much straight out of here, so you'll be able to also use this to study. Right. First things first, what is a sine wave? A sine wave is a measurement of change shown by a line moving from 2 points vertically and horizontally, usually traveling right. It should be traveling right. Um, the point vertically is its amplitude, or the strength behind it, and its point horizontally is its time. And sine waves are used in various applications, but for our purposes as electricians, they can be used to measure voltage and amperage over periods of time. So, we're going to kind of rapid fire through a couple of these, and then I have a demonstration to give to go along with this. So, sine waves and circles. There's a relationship between sine waves and circles that is pretty important to remember. A sine wave is measured in degrees of a circle ranging from 0 to 360. The center of the sine wave is 0 or 180, and the peak is 90 or 270. Um, the way that I like to think about it is a sine wave is two half circles, as I said. So you can think of a sine wave being two half circles, as any value above 179 can be thought of as negative. So, yeah, as I wrote down here, 0 and 180 are at the same point in terms of their amplitude or strength. And technically, the same thing goes for 270 and 90. They have the same strength behind them. It's just that they're both going in different directions. Whereas 0 goes to 1, 180 goes to 181, which can be thought of as negative 1. So it can be a little tricky, but I personally find this as a pretty easy way to remember it. Um, Obviously, to each their own, but yeah. Continuing on, here's a GIF or whatever graphics interchange format file um, that kind of displays the relationship between your sine measurement, which is your angle, and its like peer position on a graph. So what we're focusing on here is the red line. You can see as the circle makes its rotations, it follows that. So when it hits 0 and 180, it's at the center line here. And then when it's at 270 and 90, it's at the top and the bottom, respectively. Or bottom and top, respectively. I forgot what order I said that in. And again, you can also see that up here. This symbol here, this 0 with the line through it, is referred to as theta. Um, it's just a algebraic term for the angle that you're referring to. We really haven't dealt with it, but it's good to remember just to keep that in mind. Usually theta can be also represented by whatever angle you're measuring. So for example, if you're measuring A, instead of doing sine of theta, you could do sine of A. And here's where I wanted to show a little bit. We're gonna go back and forth between this, but so this is a tool called Every Circuit, which allows you to set up digital representations of electrical circuits. So what I have right now is just a very simple circuit. It is an AC generator, a light switch, a lamp, and a grounding point. They're all connected together to form a complete circuit. When I hit this, I'm gonna just let it run for a little bit, and we can watch these blue lines here. Now, as they go down, the green boxes start moving faster and faster, and as it goes up, it gets slower. This is to show how your strength increases with your distance from your center, essentially. It gains more strength the further from center and loses strength as it gets closer. So that's why we talk about it in terms of circles, because right now it's at 0, then it comes up to 90, then as it hits 90, it starts to taper out and go back to 0 or 180, hits its bottom peak of 90 or 270, and then it starts to slow down again, comes back, hits 0 again, or 360. Now, the other thing to remember too is obviously power can't flow if there's no complete circuit. So if I open the switch here, this one continues to go, but there's no sine wave to be measured here because there is no power, or no voltage to push power, essentially. Now, why do we use circles? Circles are used to represent sine waves due to how AC power is generated. Most of the world's AC power comes from turbines, which are a generator. Which essentially the way it works is a turbine has a set of fan blades essentially that get pushed around by steam, which then spins a part of a generator called a rotor, which spins the shaft, and it has, I believe, it is a set of copper wires on there that help form an electromagnetic field, and then as the field is formed, it cuts through what are called lines of flux, which are essentially the lines in a magnet. But yeah, that all is just a little bit above our pay grade. So the good way to think about it is we use circles because a generator and a motor, for example, both spin in circles, and those are our two different ways of interfacing power between electrical and mechanical energy. In a generator, it turns mechanical energy into electrical energy, and a motor turns electrical energy into mechanical energy. That's basically the simplest way that I can put it. Why do we use AC power instead of DC power? Now, we use AC due to the fact that we can step up and step down AC power using induction, which we talk about in, I think, the next unit we start talking about induction, and then later on we talk about induction specifically in AC circuits. Now, the way that induction works is, I'm not going to get into that right now because it's just going to cause a little more confusion, but the other big reason for using AC over DC is because we can convert it into DC, but not the other way around. Using rectifiers, which are essentially combinations of diodes put together to prevent the power from going back and forth and alternating. It turns it into a direct current source, which, like I talk about here, you use an AC adapter to plug into your wall, which then adapts it into DC power. So that, for example, my computer can then use that DC power. Or, my monitor, my phone, stuff like that can use that DC power. And that process is called rectification. Now, there's a couple different ways of rectifying. The two important ones for us are full wave and half wave. As I explained here, a full wave rectification converts the negative AC volts, which, again, that's why I brought it up earlier, how you can think of negative AC, or volts from degrees 180 to 360 as being negative instead. So it turns what would be negative voltage into positive voltage, essentially. So it just removes that negative sign from the front of it. Again, kind of why I explained it that way. And then half wave, instead of converting that negative voltage into positive voltage, it just gets rid of it completely. And, we go over this a little more later in the presentation. Now, how is AC voltage measured? Obviously, you can talk about, like how we physically measure it using voltmeters, but the way that the voltmeter calculates it is by finding the average effective voltage of a sine wave. This is what we went over this morning when she talked about how peak is your maximum and RMS is your effective, because you're not, like I think I explained it here, and I think back in I think I explained, a good way to think of it is, a generator can spin varying amounts of electricity, but because it spins so fast, we don't measure the varying amounts. We don't measure the peak. We don't measure it at 30 degrees or something like that. We measure it at what is the most common, which is our RMS, or our root mean square, which, again, that's effectively your effective voltage. And you find that by taking your peak by half the square root of 2, which is 0.707, and And then you do the opposite to find your peak if you have your RMS, which is the 1.414. And yeah, as I explain it here, your peak is your maximum, your RMS is your effective. And it's your most often it's the value you have most often, essentially. Um, the big thing though is don't get your RMS being called your effective average, as I am explaining it, mixed up with your actual average voltage, because your average voltage is gotten from converting your AC volts to your DC volts using a rectifier, which is what we were talking about a little earlier. And obviously the voltage depends on the rectification process. If it's half wave, you don't get all of it. If it's full wave, you get the full amount, just in all positive. Which, yeah, I explain here as well. Your average is 0.9 of your RMS, or 0.637 of your peak. And your half wave is then that 0.9 divided by 2, or 0.45. I don't have the full number for that, but I don't think we really need to worry about half wave rectification on this test. But anyways, frequency in hertz. This is another one that Angelia said that I should add to this. Essentially, when a sine wave completes a full 360-degree rotation, that's called a cycle. Again, that's why we use circles for this. The frequency of a sine wave is the amount of cycles it completes per second and is measured in hertz. Going back to this chart here. Currently, I have this set to 60 hertz, which, as I say here, standard frequency in the US is 60. But, it's not going 60 times a second. That's because, to make things a bit simpler, I have this running at 1,000th of a second. That way we can actually see things being simulated. If I were to crank it up, that's way too fast to see. But that's 50 milliseconds, which is, I want to say, like 1/20th of a regular second. And as you can see, compared to the other one, there would be points where the light would go a little dark. But, even at a fraction of our actual speed, we move so fast that that light essentially maintains its on position the entire time. So that's kind of, yeah, unfortunately that's the downfall of this software, that I can't get the full per second. But simulating it in this way allows me to more readily explain, how the sine wave works without needing to, completely pull things apart, I guess. Don't really know how to phrase that best, but I think you get the point that I'm making. So, like I said, the standard frequency in the United States is 60, and the rest of the world it's 50. Why we do this, I don't know. Yeah, that's about it for that. So, for finding your voltage at points in a sine wave is where we use the sine measurement that we learned in trigonometry, which that is something that we never really got into, but that how we can actually practically apply our trig. So let me quick pull up. Okay. So say we have a simple line here. We have our sine wave. Should ignore that part there. What you can do is, so you start here at 0, let's say a second in. Then say your peak here is 2 seconds. Okay, that's a period of 1 second between them. Now, say here you're at 0 volts, but then here you're at 170. See how this forms a triangle? You can use some of these measurements to turn it into a triangle, and then that's essentially why we use the sine function. Because here we're finding the opposite, so our peak potential versus the hypotenuse, which is our total gain. It's a vector. It's magnitude and direction. So that's why we use the sine, because this would be a sine. This is our opposite, hypotenuse. Yeah, again, we went over this in AC Unit 14, and we went over this in the video about trig that I should have posted before this one. But I think that's a pretty simple way of thinking about it, about why we use the sine function. But yeah, I explain it here, in more practical terms rather than the why. For finding voltage in the sine wave, you can do by finding the point that you're measuring at, which can be a degree value. So, for example, bringing this back up, you could say like right here, oh well, this is like 60 degrees. So you can take your sine of 60 times 170 to find, maybe 130 volts or something like that. Let me actually do that math, make sure that I'm right here. Yeah, okay. So it's if you do 170 times sine of 60, that's 147. So that's at 60 degrees into the rotation, you have 147 volts, basically. Um, the value of the point can be inserted in the formula peak times sin equals instant voltage. That's what I just went over. If you have your instant voltage in sine, however, you would divide your instant by your degrees. So once again, going back to the calculator, and I'll just pull the calculator up on my computer so you can see the one I'm talking about. So let's take this 147 divided by 60. No, I did that wrong. 147 divided by... we're doing this, aren't we? So if we're at 60 degrees, sine times 147. Oh, I have to do that by division. All right, you get the point here. It's yeah. So it would just be 147 divided by sin 60. Sorry, the Windows calculator sucks. Just full stop. So that's why I was having that difficulty showing. But it gives you about 169.7, which, yeah, it's basically just 170. I just cut off some repeating parts, which, yeah. So you get your max voltage at that point. Now, if you have your max and your instant, you would divide those. So we try the Google calculator. This isn't the Google calculator, but this will work fine. So if we do 170 divided by 147, that equal... I flubbed that one. Okay. 170 divided by 1... No, it's the other way around. Damn it. Okay. So that gives us this 0.864. We take that times arcsin, which is the opposite of sine. And that gives us 59.76, which comes out to 60, which we're looking for 60 degrees at this point. So that comes out to being true. So again, that's basically how you go over finding points in your sine based on, what values you do and don't have, which again, I go over it a little more, or I go over a similar process more in the trig video. But, this is a good place to start. And yeah, but anyways, this should be out either after or around the same time as the trig video. So, hope you find it useful. I'm also going to be making a video on Blueprint, I believe. It just depends on how busy I get tonight, because I also have to write a paper. But, we'll see what shall come. Thank you for watching.